So we're now going to turn our attention to situations where things are rotating rather than moving through space, or what we call translating. So instead of translational motion, we'll be looking at rotational motion, and we get to redo pretty much everything we've done up to this point this year in a rotational setting. So hopefully it'll be a nice little review to see how all of these ideas fit together. So let's start out by redefining our kinematic quantities. So in linear or translational motion we had displacement, and now we're going to have angular displacement. Same idea where it's describing your location, displacement, but now we're doing it in terms of your angular orientation rather than your orientation in space. So if we define the x-axis to be not x equals 0, but that location to be theta equals 0, then you can measure all of your angles with respect to that location. And if you have some angle 1 here and then another angle 2 over here, the difference between those angles is going to be your displacement. Just like before, the difference between your initial and final positions we called your displacement. Alright, here we've got your angular velocity. So rather than being meters per second, velocity, should finish writing this, we are now looking at your angular displacement over time, and the angles here are typically going to be measured in radians, so this is going to be measured in radians per second. You can use degrees, and which we have done up to this point this year, but radians are actually going to be nicer to use for this unit. So we can define the average angular velocity. The symbol for angular velocity is omega. Or we can look at the instantaneous angular velocity, which is where the change in time goes to 0. And so we have the same relation before, that it's the derivative of the angular position gives us the instantaneous angular velocity, just like before it was the derivative of position that gave us the linear velocity. And moving right along here, instead of having acceleration, you guessed it, we have angular acceleration. And we can find the average by doing the change in velocity, change in angular velocity over time, or the instantaneous, again, is the derivative of our angular velocity with respect to time. So nice and analogous, same ideas, but we're just defining things differently. And one of the reasons we do this is, you'll notice if I'm considering a point on the wheel at this location versus a point at this location, and then it moves over here as the wheel rotates, all of these quantities are going to be identical for those 2 points, because the object is a solid object, so they will all rotate through the same angles and at the same angular velocities, and if they're accelerating, they will have all the same angular accelerations. So rather than considering the different accelerations at different points or different velocities at different points, we can describe the motion of the entire object with these quantities, which can be quite useful. If we assume that we have constant angular acceleration, we can define analogous kinematic equations, analogous to what we had before. I'm not going to go through the derivations again. It's identical to the derivations we had for our kinematic equations for constant acceleration. Typically I would write these with deltas here, but if we assume that your initial location is 0, then you can leave the deltas off. Delta there as well, usually. Also, our initial position was arbitrary, whatever location you wanted to call 0. It's really the changes in position that matter, and that's true also with the angular quantities. Sometimes it's useful to call the x-axis an angle of 0, but you don't have to. You can choose any position you want to be your origin, so to speak. Here we have another way of writing the average velocities in terms of initial and final over 2. Often we would write this, rather than just writing this equation, we would say that displacement is the average velocity times the time, which was going to be this guy times time, and we could do the same thing over here. I won't bother wasting time with it, but same idea. Okay, now we can jump back and forth between these new angular quantities. Okay, so we've got theta, omega, and alpha, displacement, velocity, and acceleration. We can convert back to linear or translational quantities simply by multiplying by a nice factor of r, where r is the radius or your distance from the axis of rotation. So L, that's going to be this length right here, your arc length. And all you have to do to find L is take the distance you are from the center times your displacement. And in this case, the distance will matter, because if you are closer to the center, you're going to have a smaller arc length that you travel in. So we need that. Well, r is going to matter now. Also, as you're going around the circle, you are going to have a tangential velocity. That tangential velocity will be given by r times the angular velocity. You'll also have a tangential acceleration given by r times alpha. I will mention that when you're using these kinematic equations here, you can use, for instance, on velocities, angular velocities, you can use radians per second, or if you'd like to convert and use degrees per second, that's all fine as long as you're consistent and always use degrees or always use radians when you're doing these calculations. When you're switching back and forth here, though, these equations only hold when you're using radians. So no degrees here. And the reason for that is degrees are a unit, and radians, we say they don't count as a unit. So if I multiply, these are going to be length units here, right? So I'll have meters, and if I multiply that by degrees, I'll have meter degrees, and I don't want a length in meter degrees. But if I have meter radians, radians don't really count, and so that just gives us meters, and similar things can be said for these other quantities here, right? So we're going to have meters, and this is going to be radians per second, and the radians don't really count. We say they're not really units, so you get meters per second. And just this expression here doesn't hold geometrically if theta is not in radians. By definition, theta has to be in radians for that to work. Alright, now you might have noticed that I wrote tangential here and not on the other ones, and that's because when you're moving in a circle, we learned during our study of circular motion that you also have another acceleration. This acceleration here is in the direction of, it's tangential, right? So if you're spinning up, then your acceleration is also going to be in the direction of your velocity. I'm not coming off the arrow there. So there's going to be alpha. If you're slowing down, even though you're rotating this way, you could have an alpha in that direction. But it's always tangential to the circle you're spinning in. But if you're moving in a circle, we mentioned earlier that you also have a radial or a centripetal acceleration. I tend to call this centripetal, but I wrote it as an R here to match the diagram. And we knew from before that our centripetal acceleration is v squared over r. And if we plug in our new definition relating v to the linear velocity to the angular velocity, which was r omega, then we square that, one of the r's cancels out, and we can also find our radial or centripetal acceleration by doing omega squared times r. Now if we jump to a little demonstration here just to think about these ideas a little more, here we've got a ladybug and some kind of gross green beetle here on a turntable, and if we get this guy moving, come on, move for me, thank you. If we're at a constant velocity, we don't have a tangential acceleration at all. If this thing is speeding up or slowing down, we do. But we will always have a centripetal acceleration, and that centripetal acceleration is omega squared r. So as r is bigger, the beetle has a larger r, it's farther from the center, then it's going to have a larger centripetal acceleration. It's also going to have a larger tangential velocity, right? Because that's r times omega. Omega is the same for both of these guys, so it's going to have a larger velocity. By omega being the same, we mean that they both go around the circle in the same amount of time. They have the same change in angle per time. So there you have it. jumping back to our diagram here, so you don't always have tangential acceleration, as I already mentioned, but you can. But you always do have radial acceleration or centripetal if you're going around a circle. If you have both of them, you could say that your total acceleration is the sum of these two things. So if I take that guy over here and add that here, then my total acceleration is going to be this vector here. Now keep in mind it's the vector sum, so the total acceleration is the radial acceleration plus the tangential acceleration, and you have to add these as vectors, right? So you would need to do, if we were doing magnitudes, we would say the total, not total acceleration is the square root of the magnitude squareds of these guys, right? So don't just add the two numbers together. Vectors don't work that way. And speaking of vectors, we have these new angular quantities, and what is the direction? Because they are vector quantities as well. And the direction is kind of strange. Here is the rule, and it's just a convention. If you take your right hand, and you have to use your right hand, otherwise you'll get the wrong direction, and you curl your fingers in the direction that the object is rotating, then your thumb will point in the direction of the vector. I know that doesn't make a whole lot of sense, but if it's rotating this way, the displacement will be a vector pointing that way. The velocity will be a vector pointing that way. The acceleration, if there is any, if this is speeding up, the acceleration will point up, and if it's slowing down, the acceleration will point down. And you just need to keep track of positives and negatives in this regard, so that all your kinematic equations will work out fine. Whether it's really up or down really doesn't have a physical significance, but we do still ascribe it a direction according to this right-hand rule. Alright, let's jump into some examples. Start out with something pretty simple. We've got a hard drive rotating at 7,200 RPM. So we do have to be careful how to convert revolutions to radians and all of these things. So 7,200 revolutions per minute, that's an ugly 2, but revolutions per minute, that is not the angular velocity. Angular velocity is what we're trying to find. You might want to make note of that. This is essentially a frequency. Normally frequencies are given in revolutions per second though, so we do want to convert this. In 1 minute there are 60 seconds, and so we get 120 revolutions per second, or 120 hertz if you will. So there's our frequency. Well, how do we relate the angular velocity to the frequency? Well, angular velocity is going to be, we need radians per second. So if we have 2 pi and the units, well, I'll just put the equation here, 2 pi times the frequency. So 2 pi is going to be radians per revolution, and then the frequency is revolutions per second, so revolutions cancel out. So this is how we convert. You probably should jot that equation down in your wonderful notes that you're taking. This is how we convert between a frequency and the angular velocity. For those of you who are crazy like that, you could also say this is tau times the frequency, though I wouldn't recommend it because we're going to use tau later for torques. Anyway, so we want to get to omega here, so all we got to do is take 2 pi times our frequency of 120, which works out to be approximately equal to 754 radians per second. Okay, so you need to be able to convert between these different quantities. Alright, next up we have a carousel, like a merry-go-round thing, and it has a constant angular acceleration, increases its velocity for 8 seconds, blah 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 blah, and we want to determine a whole bunch of things. So it's a good idea, just like before, to list the quantities that you're given. So we've got alpha is 0.06 radians per second squared. We've got our initial angular velocity is 0. We've got a time of 8 seconds, and we want to know the angular velocity of the carousel, so we're looking for omega. So similar to before, we could also look at the quantities we don't care about. In this case, we don't care about displacement. So the kinematic equation that doesn't have displacement in it is going to be v equals v naught plus at. Kind of screwed that up. In this case, we're going to say omega equals omega naught plus alpha t. So omega naught is 0, alpha is 0.06 times our time of 8 seconds. And we get a wonderful 0.48 radians per second squared. Nope, not second squared. Sorry. There we go. Finding a velocity. Alright, next we want to find the linear velocity of a child 2.5 meters from the center. So that just gives us r. And the equation to relate linear velocity to angular velocity is r omega. So all we have to do is multiply this 0.48 that we got in part A times 2.5, and we get 1.2 meters per second is the linear velocity. Tangential acceleration, that one was r alpha, and we were given alpha, so all we have to do, these are pretty tricky problems, I know, we have to do is multiply that alpha by the r, and we're going to get 0.15 meters per second squared. Moving right along, centripetal acceleration. We could do v squared over r because we have v, but we might as well use our new equation just for fun, which was omega squared times r, because we also have those quantities. Omega is 0.48. Square that puppy, multiply by 2.5, and we get 0.567. This one is also meters per second squared, so both tangential and centripetal will come out in meters per second squared. Total linear acceleration, we just have to add these two, but add them like vectors. So square root 0.15 squared plus 0.576 squared, all of that goes under the square root, and that works out to be 0.595 meters per second squared. So not too bad, but it is, a bit more to keep track of, so be careful with your bookkeeping, so to speak. One last example, and then I will let you go. So we're going to look at an example where we have the angular velocity as a function of time. At 2 seconds, what is the angular acceleration? So to find angular acceleration, we can take the derivative of our angular velocity. So we take the derivative of each term separately. This guy's a constant. The derivative of a constant is 0, so that goes away. And then we have 1.2t, which just becomes 1.2. So this is constant acceleration, radians per second squared. So we don't really even need to worry about the 2 seconds because it is constant. It's 1.2 at any time, so there's that. Now we want to find the speed and the components of the acceleration, so that means the tangential and the centripetal parts of our acceleration. Starting out, we'll find speed v, which was r omega. Here is where the 2 seconds is going to come into play because omega is changing with time. So that's 2.5 times 1.6 plus 1.2 times 2. Throw all that in and multiply, and you come out with 12 meters per second. So moving quite quickly. Then we want to find our tangential and centripetal accelerations. Our tangential is going to be r times alpha. R is 2.5. Alpha was a constant 1.2, and so that works out to be 3.6 meters per second squared. And then we're not going to add them together, we're just going to find the two components. So now I find centripetal acceleration, which is going to be omega squared r. I guess I should have calculated out omega first. So omega, this was going to be 2.4 and 1.6. So this just came out to be 4. So we're going to have 4 squared times 2.5, not 2.5. That was from the last one. Okay, I lied. Okay, this should have been 3. It still comes out to be 12 because this was 4 and that was 3. I looked at that part on my notes. Anyway, 2.5 was the radius on the last one. Now we're at a radius of 3, so this is also 3. There you go, fixing everything in the end. So we're going to have 16 times 3, which is 48 meters per second squared, which is quite a large acceleration. And we have these two different accelerations. As we're speeding up, this tangential acceleration is not increasing, because that's essentially the rate at which your velocity is increasing. And even if you're going really fast, our velocity is still increasing at a constant rate. This, on the other hand, is sort of the rate at which you're turning. So as you go faster and faster, you're turning more quickly as you go around that circle. So this guy is going to continue to increase as you speed up, whereas this guy is constant. All right, that's all there is. See you next time.